Now we're going to wrestle with a classic in relativity theory, namely the twin paradox, and we'll take the example that we already started with and extend it a bit. Now we say that Rocky and Steve, they start at home together, but Rocky, he travels in his rocket 4 light years away at 80% of light speed. Then he turns and travels back home again at the same speed. So if Steve then measures how long did this trip take from you left until you returned, well, then he will say that you traveled at 80% of light speed, 4 light years. That takes 5 years, since 4 is 80% of 5. And it took 5 years back, so the whole trip took 10 years. Whereas we saw Rocky, he would measure that it took 3 years to go out and 3 years to go back. So he says that the trip took 6 years, and it will also be the case then that Steve has gotten biologically 10 years older, and Rocky has gotten 6 years older. We can draw this in this figure where we have a vertical axis, the y-axis for time, and then the horizontal x-axis for space. And so I've put in here 4 light years. That's when Rocky travels out and goes back. And Steve, he's just sitting still, so he's not moving in space, so he's just following this time axis vertically. And when Rocky starts returning, then 5 years has passed, and when he comes back, 10 years has passed for Steve. Whereas I put in these blue dots to mark one year as Rocky measures it. So he measures 3 years, 3 blue dots, and then 3 more dots on the return trip. So he would say where we have the number 10, it would be number 6 then for Rocky, as he measures his trip. So far, there is no paradox, since the paradox is supposed to be a seeming inconsistency, but there's no inconsistency here. We're just saying that Steve gets biologically 10 years older because processes are moving faster in his body than for Rocky, who has gotten biologically 6 years older. And both could have agreed that 10 years have passed on Earth, in the sense that the Earth has rotated 10 times and it's been Christmas 10 times. What makes this is a paradox into a paradox is that the theory of relativity says that it's relative who stands still and who moves. There are just all these reference frames, but there is no absolute reference frame saying you are actually standing still and you are actually moving. It's up to us to choose. Either we say you are standing still and someone else is moving relative to you, or we can say the other person is standing still and you are moving relative to them. There is no correct answer to who is standing still and who is moving. So it would be equally correct to say that Rocky is standing still in his spaceship and Earth is speeding away at 80% of light speed. But then the paradox is, if we are saying that the person moving becomes younger than the person standing still, we can't say that, well, they could both be standing still and both be moving, and both could become younger than the other. That would be inconsistent to say that when they meet, each of them is younger than the other. That can't be true. So there's the apparent paradox, but this paradox is not a real contradiction. It's just an apparent contradiction. So there is a solution to this paradox, and we are going to look now at what the solution is. So then, when Steve measures how much time it takes for Rocky to travel, he measures that Rocky travels 4 light years in 5 years, moving at the speed of 80% of light speed. But what happens if we say instead now, no, Rocky is not moving, Rocky is standing still, and it's the Earth that's moving away at 80% of light speed? Well, then Rocky will be sitting still, using his frame of reference to measure, and after 3 years, he will say, oh, now the Earth has moved away at 80% of light speed, and 80% of 3 years, that's 2.4 light years. So now the Earth has moved 2.4 light years away from me, traveling then at 80% of light speed for 3 years. If he wonders then, well, what's the proper time that has passed for Steve? He can measure that using this formula that we looked at in the previous video. Rocky can take the coordinate time in his frame of reference. 3 years has passed, and square that. Then he can take minus the distance that the Earth has been speeding away, and that's 2.4 light years. So we can take 3 years squared minus 2.4 light years squared will give him 1.8 years squared of proper time. So he can say, well, now that I measured 3 years having passed for me, Steve will have measured using proper time that 1.8 years has passed for him. So what this means then is that they will have reference frames where it's different what we say happened when we ask what is happening now. Then Rocky will say that when it's now 1 year has passed for me, only 0.6 years has passed for Steve. And when my trip has lasted for 3 years, only 1.8 years has passed for Steve. So that's called the relativity of simultaneity. It's relative to different peoples and different reference frames, what happens simultaneously or at the same time. And what we see here then, the solution to this paradox is that when Rocky turns, he changes his own frame of reference. So he observes or measures what Steve experiences at the beginning and at the end of this period when Steve is sitting home. But there's a gap in the middle that Rocky cannot observe, cannot measure, because he's changing reference frames. And because the universe just acts in this way, that it adjusts speeds, distances, and according to what reference frame people are in order to make it the case that everyone measures the same speed of light, but it has these strange consequences. So here's another way of explaining what happens when people are in different frames of reference. Here I've put 2 coordinate systems on top of each other, one gray and one red. And the green line, that's light. So we have time going on the vertical y-axis and space on the horizontal x-axis. And you can see that if you look at the gray system first, after 1 year of time, light will have passed 1 light year. And after 2 years of time, it will have passed 2 light years. 3 years of time, it will have passed 3 light years. So the green line will cross coordinate 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, because light travels at 1 light year per year. But if you look at the the red reference frame, you'll see again that here also light moves at light speed. So after 1 year, it will have light will have traveled 1 light year also in the red coordinate system. But if you look at 5, 5, the coordinate 5, 5 in the gray system is equal to the coordinate 4, 4 in the red system. And the point is that when people are in different reference frames, they will measure time and distance and length, etc. in different ways, but they will all measure the same light speed. So the universe then contracts and adjusts and changes time and size for different people and different observers in order to maintain that light speed is the same in all the coordinate systems. Why is the universe relative in this way? Why does it make sure that everybody measures the same light speed, but that time and distance become different when we measure in our frames of reference? Why would the universe do something so strange, and just when it comes to light and not other kinds of motion of things that has mass? Well, if you look around, ask experts and look in books and etc., there is the common answer is that's just the way it is. There's no recognized theory or the common theory. This is the theory that most experts follow, etc. Beyond just saying that's just the way it is. There is no explanation to this fact. Now, this is a video series for a book called The Basic Theory of Everything. So, of course, we have to suggest answers to all questions. So I'm going to suggest also an answer to this question when we get to the video called Why Do We Have the Laws of Nature That We Do? But the answer to this question will have to wait until that video. So far, we are just looking at still looking at consequences of what it means living in a universe where everybody measures the same light speed. And this is one of those classics. Then is the twin paradox, but which then has a solution. There is no inconsistency in the theory of relativity. It works just fine to explain also how we can have these strange results that we see in the twin paradox.